today about limiting and excess reactants, all right? And a couple of definitions before we get rolling in some examples and some calculations. So I'll just let you write that down. In the chemical reactions that we've done so far, either it's been a decomposition reaction like the one that you did on Friday, where you have something like, it doesn't matter, A, B, decomposing into A and B. And if I were to give you a mass of that particular substance, you could easily go through the motions and figure out how much of the product I would expect to get. And in this case, when there's only one reactant, there's no real need to have this discussion about excess or limiting reagents or reactants. But there have been a couple of reactions where we have two reactants becoming products, whatever it is, and I would give you a number, and then in the question, and you probably don't recall because you just would have grabbed that number and started calculating, but in the question, we would describe the other reactant as being in excess, all right? In other words, what we mean is there's plenty of it. So when this 5 grams of A is gone, lots of B was there for the reaction to proceed, and therefore all we had to do was worry about the 5 grams, all right? In today's questions, we're going to give you numbers for both A and B. We're going to give you 5 grams of A and maybe 4 grams of B. And the question then becomes, which one of those two numbers do I use to answer the question? There can't be two answers to the question, so one of them has to be one of the numbers that we're going to use. And the answer to that is we use the limiting reagent or the limiting reactant in order to solve that. The limiting reactant is the thing that runs out in the process of doing the chemical reaction. In any manufacturing process, you can have this excess and limiting reagent situation. Sometimes when I've taught this, I've used manufacturing bicycles as an example. If you were a bicycle manufacturer, then you need a bunch of wheels, and you need some frames and some handlebars and some seats. Okay, and then you need a bunch of little tiny parts. But if you were to imagine that those were the main pieces, and you ran out of wheels, but you had lots of everything else, then your manufacturing process would have to stop until you got more wheels. The reaction would be limited by the number of wheels you have because you ran out of wheels. So there's always a reactant that is completely consumed by the reaction. There's none left over at the end. It brings the reaction to a halt because there's nothing left for the other reactant to react with. And we say that it's the limiting reactant. It limits how much that can be formed in the reaction. When we do our calculations, it's that limiting reactant. That's the number that we use in order to solve it. All right? Now, in the past, again, like I said, I've used bicycles to try to illustrate this. I've even used sandwiches to illustrate this, right? But I've come up with a far better example than any of those. Not necessarily better, but one that I like better. And that is making Lego fighter jets, right? Because if you are preparing to do battle with, say, a sibling, you need as many Lego fighter jets as you can have so that, you know, if you've got more, then you defeat him because you destroy all their fighter jets. So to make a very economical Lego fighter jet, you need 4 2x4 bricks. Everybody knows a 2x4 brick, the classic Lego brick. So you need 4 2x4 bricks. They go together like this, all right? I was mocked this morning. They said I was just making stairs. It's not stairs. They're fighter jets. Colors are not important, but if you can color coordinate it, it is nice. So there's the 4 2x4 bricks put together like that, and then 1 2x2 brick, and I don't have another color coordinated one, so go with this one, to make your standard fighter jet. See that? You can even imagine it, can't you? Anyway, you don't have to make that sound effect. But that's a fighter jet right there. Then you place it on the edge of the table in a nice angle like it's getting ready to take off on the aircraft carrier. And you've got your standard fighter jet. All right? So let's write a reaction for the building of fighter jets. I'm serious. We're going to do that now. I was going to do it on the board, but I'll try to do it on our little note here. So sandwiches, they're out. We don't care about sandwiches. So out with sandwiches. So here we got our fighter jet equation. 4 2x4 bricks. 1, 2, 3, 4. 1, 2, 3, 4. No? Not good? Okay, we could write 2x4 plus 1. We don't normally write 1. Yeah, I want you to write this down. Don't you know how to draw Lego bricks? Jeepers. And this is just a 2x2. Wasn't very good. It's supposed to be square. There's my 2x2 brick. Horrendous 2x2 brick. 2x2. And that produces 1. And I'm just going to write jet because I'm not going to attempt to draw that fighter jet. So we've kind of set up this ratio of parts. You just don't look impressed out there. This is a fun example. Jeepers. So now I need some volunteers. Volunteers? Kristen, that was an arm up. That was a stretch. Yeah, come on. That was an arm up, Kristen. Come on down. What? A total decline on the volunteers. I need some volunteers. Come on. All right. 1, 2. Good. And I happen to have parts to fighter jets. Come on around. And if you could now separate out those parts for me, that would be great. I need the 2x2 separated from the 2x4s. Already grouping them to make fighter jets? That's crazy thinking right there. And then you're going to count them up. How many 2x4s? You've already got, how many? 38?
I think so.
That's no good. I had set out 40 of them, so my example would be good. All right, give me 2 of them.
You're missing 2.
Yeah, I know. I hit that. Okay, now they're gone. 30. Count again. 36. Right? 36. 36 bricks. How many 2x2s? 23. 23 bricks. All right. So, in this case, our bricks represent moles. All right? And I put them down in the mole line. And that's because we're talking about individual entities, right? We're talking about almost like molecules or atoms or the pieces that we build our molecules out of, with the jet being an entirely built molecule. And so we could have dealt with grams. We could have had a grams line. What would I have needed to know in order to determine the total mass of my 36 bricks? Yeah? The mass of 1 brick. If I knew the mass of 1 brick, I could use that as a conversion factor and figure out how many, what's the mass of the 2x4s and what's the mass of the 2x2s. All right? That would be like a molar mass if I had the mass of a 2x4 brick. We could actually turn it into a lab if you thought that this is boring. An entire lab of this would just be excruciatingly boring. So I'm not going to drag you through that. But we could have had masses. We could have turned masses into bricks. But let's just think in terms of these individual bricks. So the next question is, how many jets can we make? 10? 10? Then count. So now, that's great stuff. What? Would anybody like to answer what? If she can make 10 bricks, she's got 40 bricks. You see the? Okay. All right. Well, that's important stuff. That's important information. So we'll take care of that. Let's switch that now to 40 bricks. So I had 42 bricks. Obviously, I was 2 bricks short. Forget about it. Anyway, let's continue. How many fighter jets can we make? 10. Why can we only make 10? We've got 23 of the 2x2 bricks. Yeah, because the 2x4 bricks are limiting. We're going to run out of the 2x4 bricks if we were to build jets for every one of these, and that's what I'm trying to illustrate here. Very straightforward. All right, so we're going to end up being able to make 10. We're going to be able to make 10 fighter jets, 10 jets. How many of the 2x3 or 2x2 bricks are we going to use up? We're going to use up 10 of them, right? Now, let me just go over what we're doing here mathematically. We can easily figure out that we need 10 bricks. 10 bricks needed. All right? And this is exactly how we answer the questions when we start dealing with masses and moles. What you want to do is you want to take one of your reactants. It doesn't matter which one, but you want to take one and you want to figure out how many of the other reactant is needed. And we use there the mole ratio. All we had to do was take 40, divide it by 10, multiply by 1, and it tells us that we need 10 bricks. By looking at what we have 23 bricks. We only need 10 bricks. So therefore, I have extra 2x2 bricks. We would say that this is excess. And this then is the limiting reagent. Once you know what the limiting reagent is, you can then use it, and I'm just going to grab another color here. You can then use the limiting reagent to figure out what we're going to get. So it's like we're doing 2 questions in one. First, we figure out what we need. Then we figure out which is limiting. And then we use the limiting to figure out what we're going to get. Again, we would use a mole ratio right there. Mole ratio. So if I were to figure out what we were going to get the same way, I would take a regular conversion factor run, 40 bricks times, again, the mole ratio, 4 2x4 bricks to produce 1 jet. And in the end, we end up figuring out just what we thought, that we're going to end up with 10 jets. All right? Now I'm not going to, oops, 2 S's on there. Now I'm not going to make you make the jets I did this morning. That was good fun. But I think we get the idea. Thank you very much. I think we get the idea that one of them is going to run out and the other one is going to be in excess. Let's go ahead and do some problems. And then once we're done, like I said, I'm going to give you some time to work on this. So, again, this is a stoichiometry problem. It involves a chemical reaction, magnesium reacting with oxygen. And so we're going to still follow the setup that we used last week to solve any stoichiometry problem. What's the first thing we need when solving a stoichiometry problem? Absolute must. Got to start with this. Yep, Scott. Balanced chemical equation. Then you put your numbers underneath in the position that I've instructed you on how to do that. The difference between a limiting reagent problem and a regular problem is that you have 2 numbers in the reactants. You're given both reactant numbers. Now, I know many of you like to generalize things, so you might be thinking, oh, this is great. 2 numbers, it's a limiting reagent problem. But it's not only just 2 numbers, it must be 2 numbers in the reactants. Tomorrow we're going to do some percent yield problems. I'm going to give you 2 numbers, and one number is a reactant and the other number is a product. That's how you know that that's a limiting reagent, a percent yield problem. But if you have 2 reactant numbers, it's a limiting reagent problem. So just 2 numbers isn't good enough. You've got to paying attention to what the 2 numbers are. All right, I'll try to do this again on the computer. We'll see how this works out for us. Does somebody have the balanced chemical equation, or at least the reactants and the products? Jess, what do you got? O2 to produce 2MgO. Again, write the information you've got down. Both of these are in grams, so they go under the gram line. 6.73 grams of magnesium. 6.73 grams. 8.15 grams. As soon as you see that you've got the 2 reactants, you have to think to yourself, this is a limiting reagent problem. I need to solve it in this way. So what do? Well, in the end, if you look at B, we want to find grams of magnesium oxide. So the question becomes, which one of these 2 numbers do I use? Just like in our little example, what I need to do is, first I need to, using molar masses and the mole ratio, I want to figure out how much of O2 I need. So I'm actually going to kind of ignore the second reactant, and I'm going to figure out how much of it I need. I'm going to find out how much of the other reactant is needed. So I'm going to convert that first reactant into the second reactant. So I'm going to write that as a little note here off to the side. Convert into second reactant to find what is needed. So we've got to figure out how much is needed so that I can make a judgment on that. So I'm going to need some molar masses, Mg and O2 aren't too bad. I don't think we need to write them down off to the side. And just as before, 6.73 grams magnesium. Periodic table's out. What am I putting where? How am I going to turn this magnesium into whatever? What am I putting in what location? Some of you are calculating already. Some of you have found numbers. Jess, what am I doing? 1 mole for every 24.3 grams will convert my grams to moles. Now I need the mole ratio. That's what it says in my map. I'm treating it just like I did last week. It's as if this number here doesn't exist. For every 2 magnesium, 1 O2 is needed. Really, that's what we're translating it to. I now want to convert that into grams of O2 so I can compare it. What am I putting where? Careful, this is O2. It'd be 32. 32 grams over 1 mole. And that's going to get me the amount of the grams of O2. And because it's limiting reagent, I always write down needed. And I want you to do the same. I want you to really be focused on the fact that that's how much is needed. How much is it? John, do you got a number there? Oh, no, John doesn't even have a calculator. Who's kidding who? Jeepers. I didn't even realize, the way it wrote down needed, I thought, oh, he must be done calculating. No, he can't calculate. Doesn't have a calculator. What do we got? 4.4? So, 4.4. Now, we should actually keep another significant digit, but this isn't an answer yet, so we really don't need it. It's not a big deal. Now, here's the thing you have to do. We have to compare what we have to what we need. Now, in the past, I used to say, oh, well, look, we need 4.4, but if you start with that number, you always make a logistical error. What I suggest you do is go back to the question, circle it, think, I have 8.15 grams, draw the arrow back to it, but I only need 4.4. Is oxygen limiting or excess? It's excess. I've got more of it. I've got plenty more. That makes this excess, all right? Students will sometimes do the reverse logic. Start with the 4.4 and go back to the 8.15 and then get it backwards and think, oh no, I don't have enough O2. So please really consciously go back to what you have, compare it to what you need. If it's more, it's excess. Yep? If you were to start with this number and go back around here, you'd find that this is limiting. That this number would be smaller than what we would have got in the calculation on what we need. It doesn't matter what order you do it in. I've always simply done the first or the second just because it gets me going and I don't have to think about it, right? Right, in my mind, and I've done so many limiting reagent problems, I say, oh, I got 2 numbers, I'm going to just take this, I'm going to convert it to that, and I just start doing the problem without thinking about it. That's why I do it that way. You could do it the other way. It would not hurt it, okay? So now that we know which one is excess, then automatically the other one becomes our limiting reagent. Running out of space in there, but we'll squeeze it in. And once you know the limiting reagent, you use the limiting reagent to find the answer. So in actual fact, now my little map is going to start with magnesium and is going to go, oh, and I'm terrible at this, all the way over here. I apologize because I'm not good with this machine, to moles. And now we can go up here to the grams using the molar mass of magnesium oxide. So now we're going to be doing our same calculation, except now we use the limiting reagent. So we know that magnesium is 6.73 grams is the limiting reagent, so we'll use it. We already know what the molar mass is. We know that we're starting with 2 mg, but now we're going to this side of the reaction. We're going to the product side, 2 MgO. And now I need a molar mass of magnesium oxide. Oh yeah, 40.3. We used that a lot in our experiment, didn't we? 40.3 grams per 1 mole. Now we calculate away, and we have our product formed by using the limiting reagent or reactant. 3 significant digits, please, when we round this one. Yeah, Kristen. Sorry? 11.2 grams MgO produced. Okay? Now, as you can imagine, a question like this is going to be worth some marks. If you have to do the balanced chemical equation yourself, that's typically 3 marks, reactants, products, and balancing. And then this little run here is going to be 1, 2, 3, 4. That gets us to 7. This run here is another 4. That gets us to 11. There'll be 11 marks in that, all those little steps involved. Okay? So that's a pretty big, hefty question. Let's do one more example. Oh, and I do want to change the number here. Let's keep the 71, but let's make this 39 grams of water. I hope that's a large enough change. And I'll explain why when we get to the question. As you're writing that down, I'm just handing out the practice page. This page contains both questions for today's lesson and tomorrow's lesson. So for today, it's just the limiting reagents. Tomorrow we'll do the percentages. So again, this one we're giving you the equation. We can just put our masses underneath here. I know some of you are still writing. We'll get you caught up. I just want to write my masses in. And in the end, it asks us. I don't know what I just said there. In the end, it asks us to figure out the mass of HClO3 produced, question mark, grams. It's going to be fun. It's going to go online. Anyway. And what I expect you to be able to do the balanced chemical equation, put the numbers in, notice that there's 2 reactant numbers. Really the question in your mind is, oh, which one will I use? And so therefore it's a limiting reagent problem. Convert one into the other and see whether which one is excess and which is limiting. Which means in the end, we need that molar mass and we need the molar mass of water. That one's not too tough. And at the end, we're also going to need the molar mass of HClO3. We need all these molar masses. The only one we're not using is HCl. So we might as well do all those calculations right off the bat. Whether you do that right away or not, it's not a big deal, but we'll just take the time right here to do all the molar masses that we need. So ClO2, 16 times 2, By the way, folks, 35.5. Please, 35.5 for chlorine. Many students in a rush will round that to 36. You end up being quite far off the correct answer because of that 0.5. It's halfway, right? So it's a significant value. Please use 35.5 for chlorine. And H2O is one of those that we use over and over again. So you can just write down 18 grams per mole, and then HClO3, 16.0 times 3. And I'll take some of those masses once we have them calculated. Yeah, Jess? 67.5 and 85. And 85.4. I mean 84.5. 84.5. Make sure you're checking Jess's work. It's always fun when we find mistakes that Jess makes. So keep that in mind. We're good to go? All right. So convert the ClO2 into H2O needed, right? That's the first check. Again, hopefully you're going ahead of me. Hopefully you're not waiting for me to write it all down. Again, use the maps, right? Molar mass, because we're underneath ClO2, I'm going to use the molar mass of ClO2. I've got to put the mass on the bottom with moles on the top. We've done this over and over again. Mole ratio, what's on the bottom? 6 ClO2 for every 3 H2O. For the last conversion factor, we need the mass on the top in order to get grams as our answer. And again, be very conscientious. I want you to write down grams of H2O, and again, needed. That's very important to realize. This isn't a number that we're actually going to have or get. It's what we need. So how much water do we need? Kristen? 9.47 grams. And I completely messed it up again. Changing that number did nothing. I really wanted the second one to be limiting. You know what I'm going to do? I'm going to make a change right now to our number because I really want this one here to be limiting. I want to get rid of that 3 and I want it to just be 9. All right? So please use appropriate whiteout. And there's a reason I'm doing this because we saw it with the first one being the limiting reagent. We haven't seen it where the second one's the limiting reagent, and I really want that to be stressed. So I know you guys get frustrated when I change things, but it's important that we see the second one. Okay, so now that I've pulled a fast one and changed it to 9, which is fine, again, go back to that number here. This is what we have. This is what we need. Oh, I only have 9. I need 9.4. You can even mouth that if you want during the test. It's quite funny. And bob your head as you do it. It really is effective. What is water? Which reactant is it? Yeah, Megan? It's the limiting reagent, the limiting reactant. All right? That's what you said, right? Excellent. Automatically, it makes the other one excess. And I'm not worried about that one anymore. So now I'm ready to answer the question. Now, the reason that I wanted to use this is because this came up in the morning class. Now that this one's limiting, I'm using 9 grams of water because that's what I have to answer the question. Some people were confused and wanted to use this number. But if you use this number, it essentially is coming from this number, which means it's really coming from the excess numbers. You must use what you have and it must be that limiting reagent number. Don't get confused and use this number from the water. This is what I need. It's not what I actually have. And that's why I wanted the second one to be limiting in this example, to just kind of fortify that. So this time we're going across like this from our water. So now I need the water on the bottom. Again, the water number, what I have on the bottom, and that's a 3H2O, 3, becoming 5HClO3. And in the end, I want mass of the HClO3, so I need its molar mass, 84.5 grams per 1 mole equals. And then this is going to be grams of HClO3. It's not needed. It's nothing fancy like that. That's just how much we're going to get. Jess, what do you got? 70.4 grams. Are we in agreement on that? Okay, so those are limiting reagent problems. All right. How do you identify them? You will be given 2 reactant numbers. Your question then is, which one am I going to use? Convert the first one into the second one to find out how much is needed. Once you determine which one's the limiting reagent, use it to answer the question. All right? So at this point, you guys can work away.